It's all about where do the elements we see on our planet, where do they actually come from. So this sample is going to be used for the study of extraterrestrial iron-60 and plutonium-244. Iron-60 is produced by massive stars and by their explosions. Plutonium-244, on the other hand, is a clear tracer for the ARP process, which is a very violent neutron-rich process in the universe where all the heavy elements are formed. And we know how they are formed, but we don't know where. So the aim is to actually use the iron-60, where we know where it's coming from, to deduce where the plutonium-244 is coming from by measuring them in the same sample at the same time. So for the iron-60, the star explodes, then it takes a long time to actually travel towards our planet. Our solar system is actually collecting it by passing through a cloud. And then it actually takes only a few decades to settle down from our atmosphere down to the bottom of the ocean and then gets incorporated in these deep sea crusts. But that takes actually like millions of years because it's growing so slowly. This sample is actually from the Pacific Ocean, so it's 5,000 meters below the surface. It's actually growing around 2 millimeters per million of year. You need dated layers of the crust. So what we are trying to do is we want to actually take a profile of this crust based on how it's growing. We determined that by beryllium-10 datings. So in the machine what we are doing is we have the crust here. We mill off 4 millimeters, representing a bit more than 1 million year based on the profile we took before. So it's actually following the surface smoothly and it has the same age on the left and the right side of the crust. We can then extract the plutonium and measure the plutonium, whereas the iron-60 was already measured and extracted. With this powder, I will do quite some chemistry to extract the plutonium out of it, which is quite tricky because it's only a few atoms compared to the 100 grams of matrix, which is iron, manganese, and essentially the whole periodic table. Once it is extracted, then we can measure it at ANSTO, because they have the highest sensitivity for this measurement. The iron-60 was already measured here at ANU. So what we are measuring is iron-60 versus stable iron in 10 to the minus 15, so 15 orders of magnitude less iron-60 compared to the stable iron in the crust. That was measured with accelerator mass spectrometry here at the nuclear physics department. And that's the most sensitive technique to measure iron-60, which is single atom counting in the end, because we have the best facility for that. Well, the most exciting thing about this project is that it's the first time we have such a large sample to actually hold 25 million years of geological history in your hands and being able to actually do fun stuff with it.